Welcome to the module. I am Dr. G. Sindhu, Associate Professor and Head, Department of Mathematics SF, Nirmala College for Women, Coimbatore. Complex integration is a simple extension of the ideas that we develop in calculus to the complex world. In real calculus, differentiation and integration are inverse operations. We'll see that the same inverse relationship exists between differentiation and integration in the complex domain also. Line integral in complex plane. A complex definite integral is called a complex line integral. It is denoted by integral over c f of z dz. Here, the integrand f of z is integrated over the given curve c. The curve c is called the path of integration, and its parametric representation is given by z of t equal to x of t plus I y of t, where t lies between in a and b. The following are examples of the curve C. Here, we assume that the curve is smooth and hence it has continuous and non-zero derivatives. Hence, the derivative of z dz by dt can be obtained, and the definition of the derivative is shown. Suppose the time in parametric representation is divided into n intervals as t0, t1, etc. till tn, where t0 is A and tn is B. Then C is indeed partitioned into z0, z1, etc. till zn. On each subdivision of C, we choose any point eta I, and we can form the sum Sn. The limit of the sum is termed as the line integration of f of z over the path of integration of C, and it is represented by integral over C f of z dz. Also, limit n tends to infinity, Sn is defined as integral over C f of z dz. These are some of the basic properties of line integrals. First one, linearity. Second one, the sense of reversal. And the third one, partitioning the path. Now, let us see the evaluation of complex integral. Let C be a piecewise smooth path represented by z equal to z of t, where t lies between a and b. Let f of z be a continuous function on C. Then, integral over C f of z dz is given by integral from a to b f of z of t dz by dt into dt. Let us see the steps to evaluate the line integral. Step 1. Represent the path C in the form z of t. Step 2. Calculate the derivative dz by dt. Step 3. Substitute z of t for every z in f of z. Step 4. Integrate f of z of t, z dash of t over t from a to b. As an example, let us evaluate the integral of 1 by z over the unit circle. Here, first step, we'll represent the unit circle C as z of t equal to cos t plus I sin t. Then differentiate z of t with respect to t. Then substituting z of t in the place of f of z, and we obtain the result as 2 pi I. In the next example, let us find the integral of 1 by z power m with a circle at center at z0. Here, the curve C is represented by z of t equal to z0 plus rho into cos t plus I sin t. Then we have found dz by dt and substitute the value of the integral. And finally, we get the result that integral over c f of z dz is equal to 2 pi I when m is equal to -1 and 0 otherwise. This gives the important property of dependence on path. If we integrate the function f of z from z0 to z1 along different paths, then the integral in general will have different values. Hence, a complex line integral depends not only on the endpoints of the path but also on the path itself. Here we have an example of the integral of a non-analytic function to show the dependence on path. Thus, complex integration plays an important role in several areas of science and technology, including signal processing, control system, computer graphics, optimization, and so on. Overall, it is an important tool to solve many complex mathematical problems in various areas. Thank you for watching this module.